Okay, so now we're going to do some sample problems, just showing that we know how to identify dependent and independent events. And we're basically going to use that rule that we just talked about. Where well, we'll just see it right here real quick. So in this case, we have Antonia, and she rolls a pair of fair six-sided dice, which means 6 faces and numbers 1 through 6, right? Let A be the event that the first die lands on 5, and B be the event that the sum of the 2 dice is 6. Use the sample space of possible outcomes below. Using the sample space, answer each of the following questions. So what is the probability A that the probability that the first die lands on 5? Okay, so the first die would just have the black die be first. So that would be anyone where the black die is 5, which is this column right here. 1, 2, 3, 4, 5. There's 6 combinations with the 2 die, right, the black and the white, and there's 6 of them where the black comes up 5. Out of 1, 2, 3, 4, 5, 6, there's 36 total here. So that's 6 out of 36, so 6 over 36 is how we'd put that. So we're going to put that down. I'll reduce that, and that is 1 out of 6. What is the probability B? The probability that the sum of the 2 dice is 6. Aha! This is a little bit trickier. We've got to find out, how many in here add up to 6. Well, 1 and 5, there's 1 here, and 2 and 4, and 3 and 3, and 4 and 2, and 5 and 1. So that's 1, 2, 3, 4, 5. So there is 5 of 36, right? That's the probability. There are 5 of them that sum to 6. Any of these won't, because they start at 7 and go up, and this one starts at 6 and they get larger, and this one here is 6 here, and then it gets larger. So there's just 5 of the 36. So what is the probability A and B? The probability that the first die lands on 5 and the 2 dice add up to 6. Well, that would be, there is 1 here. The 5, the first die lands on 5. So this is a union, right? I'm sorry. This is a intersection. We want the P, A, and B. We draw the intersection where it is both A lands on 5 first, and B adds up to 6, right? So where they overlap, okay, is right here at this one spot. So the answer is 1 out of the 36. So now the question is, are the events A and B independent? Well, what do we have here? 1 times 5 is 5. 6 times 36 is 216, I believe. Let's just add that up. If we go 1 divided by 5. Oops, let's just do 36 times 6. I'm putting that over here. That's 216. So it is 5 divided by 216. And it doesn't reduce to 1 over 36, so I'm going to say no, they are not independent. Now, in order for them to be independent, I would have to have this number, 1 times 5, right? Let's see if I can draw it here. I'd have to have 1 over 6 times 5 over 36 equal 1 over 36. And that was not true, because they really equaled 5 over 216, and that could not reduce. That was not, these two are not equal. So that's what tells me they are not independent. Now, why is that? Okay, why would that be? If I rolled a 5, I'd have one chance in all the 36, all the subsequent chances is 1 in 6 chances that I could get there. So I have 1 in 36, but when I roll 2 die, I only have 5 chances out of the 36. There's not the probabilities, getting to 6 is harder, right? Getting to 6 is harder to do. Basically, that's one way of looking at it, right? It's harder to do. So anyway, let's try another one here, and we'll see if we can do it the same way. 200 students in 11th grade high school class. 40 play soccer, 50 play basketball, and 10 play both. Okay, so let A be the event that they play soccer. B be the event that he plays basketball. So what is the probability that the student plays soccer? Well, that's 40 over 200, which is over 5. What is the probability that the student plays basketball? Well, that would be, there were 50 that play basketball, so that's 1 over 4. And where am I getting that from? That's 40 over 200 right here. The soccer was 40 over 200, and that reduced to 4 over 20, which reduced to 1 over 5, and 50 over 200, which reduced to 5 over 20, and then that became 1 over 4. You can do that math if you want. Now, what is the probability a student plays soccer and basketball? Well, we know that is 10 over 20, right? Or 10 over 200, which is 1 over 20, right? Because there were 10 that plays. This is the intersection. See that question, that intersection. Probability A and B. So what is the intersection of those two sets? That's what it's asking us. So that intersection is the overlap, the kids that do both, right? And there were 10 out of 200, which reduced to 1 over 20. So now let's just think about that for a minute. Remember our rule, okay? 1 over 5 times 1 over 4, does that equal 1 over 20? And the answer is yes. So this is looking to be independent. What is the conditional probability? All right. What is the conditional probability? The probability of A, given that the student that B has already happened. What is the conditional probability of A? So the probability a student plays soccer, given that he or she plays basketball. So the way that question will be written in English, we'd say something like, a basketball player is randomly selected, right? So we're taking from only the basketball player. So an 11th grade basketball player is randomly selected. What is the probability that they play soccer as well? Well, we would say out of all the basketball players, there were 10 that played soccer, so it would be 1 over 5. 1 out of 5. Oops, I put 8, 5. There we go. That means out of the 50 that play basketball, 10 play soccer. So that'd be 1 over 5. So now, are they independent? Well, we did the little test here. 1 over 5 times 1 over 4 equals 1 over 20. We can see that the conditional probability is equal to the probability, meaning that the fact that he played basketball has no bearing on this probability. So we know that, yes, the probability of A given B is equal to the probability of A. Not no. And yes, they are independent events. Let's try one more. Here we go. Sherry has a standard deck of cards. There's 52 total cards. It contains 4 suits. Well, that I can do 52 divided by 4, and there's 13 cards in each suit, right? And there are hearts, clubs, diamonds, and spades. Each suit contains the numbers 2 through 10. Then there's a jack, queen, king, and an ace. Sherry randomly selects a card. Let A be the event that the card is a king. Well, there would be 4 kings out of the 52 because they are 1 king of hearts, 1 king of clubs, 1 king of diamonds, 1 king of spades. So A is the event that it's a king, which is 4 over 52. Let B be the event that it is a 3. Well, guess what? There's 4 as well of the B's. So we have, because we have a 3 of hearts, a 3 of clubs, a 3 of diamonds, and a 3 of spades. So A and B have the same probabilities, right? A and B have the same probabilities. Okay, but she selected a card, a single card. Now, is the probability A given B equal to the probability of A? The probability that Sherry selects a king, given that she has chosen a 3, is equal to the probability that she selects a king. No, if she's chosen a 3, then the probability that it's a king goes to 0. Right? If she's already chosen a 3, the probability that it is a king goes to 0. So they're not going to be equal. Furthermore, if they said, okay, she's going to pick 2 cards, so then after she's taken 1 card out of the deck, a 3, then the probability of getting a king increases a little bit because there's fewer cards to pick from. So they are not equal. Okay? How about this? The probability that Sherry selects a 3, given she's already chosen a king, and that's by the same exact logic. If she's already chosen a king, then we know it's not a 3, and that probability goes to 0. So this impacts, if she's chosen a king, it's going to impact the probability that she has a 3. So this is not true either. Okay, these events clearly are not going to be independent. That's what this says. It says the events are independent, and that is not true. The outcomes of the events A and B are dependent on each other, right? Because once you select that first card, the probability of a second card would change, and I'm not sure if that's what they specifically mean because it says selecting 1 card. But once you've selected a card, if you've selected a card, and you've confirmed that it's a specific number, then you can't, your probability that it's a different number goes to 0. We know it's not that. So that means they are dependent. The probabilities will change. Once one happens, the other one changes. The probability of A and B is equal to the probability of A times the probability of B. Well, let's just go over that real quick, but remember that there are 4 each of these cards, right? So the probability of A, there were 4 over 52, which is 1 over 13, and the probability of B was 4 over 52, so 1 over 13. So you would do it, something like this: 1 over 13, that's the probability of A, times 1 over 13, that's the probability of B, and that's going to be, I believe, 1 over 169. 169, I think, is the square of 13. So I would say that these probabilities, that is not correct. Okay? The probability she selects a card that is a king and a 3. Well, the probability that she selects a king that is also a 3, that is 0, really, right? This should be 0, this probability, and this is 1 over 169. So that is definitely not true. So let's go ahead and check that answer. Okay, now you see how to do these problems, okay? I'm not going to finish these with you. I want you to go ahead and get these done yourself.